the recording, that would be great. Thank you very much. And so why are we talking about geological storage today? This topic is getting more and more attention. The technologies are discussed controversially, but we're not going to focus on that during our webinar. On the other hand, authorities want to know how much energy or how much CO2 and hydrogen can be stored to use these technologies to reach the national climate goals that we all want to achieve. So estimating the potential is a very crucial task. And that's what we are going to focus on with in today's webinar. We want to provide an overview of existing methods and how to estimate the storage potential for CO2 and for hydrogen. We will showcase applications on these methods in different places of Europe. So we have three experts on these topics here with us today who will showcase those applications. If you have questions about the first three talks, then please feel free to ask anything right after each talk. After the talks, we have enough time to discuss this topic in a little bit more detail. We are very interested in also hearing your opinion from you as participants. So I don't want to lose any more time and will hand over to our first speaker, Serge van Gessel from TNO in the Netherlands, who's going to tell us about the methods and best practices for hydrogen storage. Please, Serge, if you could share your screen.
Yes, thank you, Cornelia. And just testing, can you hear me?
Yes.
Great.
All good.
Then we're going to share the screen. There we are. I hope you can see my screen. Yes. Okay. I'm going to talk about estimating and mapping underground hydrogen storage performance and capacities. A short presentation on what's, let's say, the state of art currently in Europe. First of all, what kind of reservoirs and what kind of formations and spaces do we map actually for hydrogen storage? Mostly this is salt caverns, let's say salt formations where you can build caverns, which hold a potential to store approximately 100 to 250 gigawatt hours of hydrogen. Gas fields and aquifers at a deeper level are also capable, which have a quite big spread of potential storage capacities. And then there is a more niche technology that is the building of lined rock caverns at a shallower depth, where also small amounts of hydrogen can be stored in places where you do not have the other options available. So when we talk about underground hydrogen storage, or UHS, as I call it here, we talk also about an emerging technology which has not yet the technical readiness level that we are known to have for example, natural gas storage. You can see here the various options for gas salt caverns, gas fields, aquifers, and lined rock caverns. And what you can see is that most of these technologies are currently in a large prototype stage. So having pilot projects where the injection and production is being tested. We do have already some longer experiences with town gas and with also in the United States with static feedstock storage in caverns for hydrogen. But that is not yet, let's say, the proof that we need for implementing hydrogen storage in the energy system. Now we see the first beginnings in Europe, first projects, pilot projects and demo projects being prepared. A lot of these projects are still in a feasibility study stage or in a FEED stage, so the front-end engineering and design. However, some are already operational or even tested, and that is specifically the case in Austria. United States, of course, has already existing cavern storages, and UK, for example. And there is, the town gas projects that you can see in the brown and the very dark blue colors here. Now, the demand that we see coming for underground hydrogen storage compared to what we have currently for natural gas storage or UGS, what we can conclude here from various studies is that the amount of hydrogen storage that we need to store in the end and in the subsurface is comparable to that what we have currently for underground gas storage. So this is really a significant amount of storage. The assumptions that we still need to make for 2050 are very uncertain, of course, but let's say there's what we can see as a common picture from the various studies is that the amount is comparable or even higher. And in the figure on the right-hand side, I think it's good to notice that the storage of gas is being, let's say, characterized in three ways. There's a technical working volume that is not a total, but it's the technical working volume that can be used to really inject and produce withdrawal gas. And then the withdrawal rate is very important. So how fast and how much can you deliver in a certain time period? And together these pictures also give you an idea of the duration that you can deliver that withdrawal rate. And that is very important, of course, because you talk on the one hand about peak storages that need to deliver in a few hours, or storages that need to deliver for a whole season. And you can see that gas fields in the current stage are predominantly focused on this seasonal storage. Salt caverns here, each triangle is multiple caverns in a cluster, of course, so there's a lot of variation, but they are per cavern much more focused on peak. Now, if we need to develop hydrogen storage, there are various levels where we have challenges. First of all, we have challenges on the geological dimension, which concerns how to understand the reservoir, the seal, and the overburden, and that concerns the geochemical microbial impacts, the storage integrity, and the storage performance and screening of candidates. Now, there's also, on top of that, a technical dimension, and that concerns how we develop or deploy the storage side, and that is about what kind of materials can we use that are compatible with hydrogen, what kind of well designs do we use, how do we arrange the compression and the gas treatment, but also the cushion gas that we need to inject to make the storage work anyway. Then a facility fits into an energy system, and that energy system is arranging and governing the supply and the demand of energy in different forms and capacities and sectors. And there's a market for that. So we cannot look at just the storage in itself. It is fitting in an energy system. It is providing a service. And that's all about economics and system integration. And last but not least, and maybe the most important circle for many countries, is that without any societal embeddedness of this technology, it will be very hard or even sometimes impossible to deploy it. Then we will have a lot of poor regulation or even also public resistance to develop it. So we need to assess the social dimension as well. Now, I will be very short about this slide, but it just depicts a gas storage in a porous reservoir, and you can see different parts. There's a cap rock on top of the reservoir. There's then in the reservoir itself, it is subdivided in the aquifer, of course, that is really below everything. That's the drive. There is the cushion gas that you need to have a minimum pressure to run the storage. And there's a working gas volume. That's the actually thing that goes in and out of the storage. So that's really the gas that you will have in operation. And then there's, of course, a mixing zone, which is, let's say, sometimes in communication with the cushion gas. Then there's, of course, faults often that have also kinds of different kinds of effects. And on the lower side, you can see a lot of effects that are happening in the reservoir or in the seal or in the fault zone. And we need to understand these effects in practical and in a multidisciplinary way. So that's really one of the complex things to understand. For salt caverns, we have also several challenges, but we are better I think, much better understood than the porous reservoirs. But still, we see also there's proof of microbial conversion of hydrogen into substances that we don't want to have in the storage, or the permeation of hydrogen, and also the wells and the integrity. That's very important things to consider also for salt cavern storage when you use hydrogen. Now, something about performance and capacity criteria. First of all, an underground hydrogen storage site, like a gas storage site, will be designed to meet a given demand profile. So you're not just seeking volumes anywhere to store something, but you need to make sure that the site that you select is capable of providing the expected load profiles, volumes, rates, cycling frequencies, the different type of demand, like peak shavers, long-term, or even strategic reserves. So that is very important. You need to know the demand. Secondly, the storage volume, we do not talk about total volume, but we talk about a combination of the working gas and the cushion gas volume. So the working gas being the dynamic volume and the cushion gas being the static volume. And the latter, the last one, the cushion gas, is not part of the operations. It's there for pressure support, but it defines a substantial share of the whole capital expenditure, or the capex, of your site. So you don't want to have too big cushion gas volumes in your location. Then we need to know the injection and production rates. That is far more important than for hydrogen storage than it is for CO2 storage. And we need to know what's the maximum rate for peak demand, but also the plateau rates that you can sustain for a longer period, and which defines the storage cycles and also the duration. So that is a very important part as well. And then last but not least, whatever you inject as hydrogen may become irrecoverable or lost or contaminated due to reactions or the fingering, dispersion, leakage of hydrogen in the reservoir. So that's also something to consider when you develop a site. Now, something about European screening and performance studies, which target porous reservoirs, and sorry, that's a typo, also salt cavern sites. And these are, I think, the three main studies, recent studies that have been or are being conducted. HyESPRI is looking at storage of hydrogen by converting the existing underground gas storage facilities in Europe. Then we have recently finished and also presented the high storage project, also European project, Horizon 2020, which looks at porous reservoir traps across Europe, also using the CO2 stop data that has been will be discussed maybe later on. And then we have one of the studies from Caglian et al. In 2020, which looks at the capacities for salt caverns across Europe. Now, please keep in mind that everything these studies provide is in terms of theoretical and maybe effective capacity. So the practical and the matched capacities are much smaller, because you have all kinds of surface restrictions, legal restrictions, and market restrictions. So please keep that in mind. This is just a theoretical or at best effective capacity. Now, there's a lot of other studies that I'm not going to look into today, but there's some listing here of studies that have recently provided, I think, great insights and different ways to assess the volume. I'm going to look now briefly at what high storage has done overall for the European potential traps that were identified by the project. And this is a very, very, very brief summary and a very global level of what is written in the report. So I really emphasize, please visit the site and also these reports for all the details. But in overall, there is a large database, but it is also an imperfect database. There's a lot of information missing in it, but it identifies a lot of potential traps across Europe. So these are approximated with a simple model. And then for each reservoir, you have data and sometimes missing data. So there is a use of typical assumed reservoir parameters that are being applied. Then you need to know the storage efficiency factors, and that is being derived by the project by analytical models. These are explained in detail, but with the storage efficiency factor and all the data on the left-hand side, you can provide a calculation of the total storage volume analog way for all the traps that were identified. And you can see that different formulas are being used for either deep saline formations, reservoir gas fields, gas reservoirs, oil reservoirs, and existing gas storages. So there's different ways to calculate it, but at least these elements that are on the left-hand side are used. Now, if you have the total volume, you need to have an estimate of what could be the working gas volume. And for that, the High Storage Project conducted a series of numerical reservoir models with a great variety of different settings and characteristics. And these are then used to estimate a working gas total volume typical relationship, and that is something you can also transport to the total volumes to obtain the working gas volume. So that is a way of doing it, but a lot of details and more comprehensive explanations are, of course, in the report. Now, the High Storage Project provides an overview that shows that, in fact, what the expected demand is for storage in different countries, and you can see that for optimal storage estimates in 2050, that the technical and theoretical amounts are for caverns, both caverns and onshore porous media, is much higher than what is available, than what is requested in the demand. So this is something I think is good news, but that gives you at least an overview of that. Now, very briefly, also something about the capacity estimates that are being conducted at the moment for HISPRE, and there's two reports elaborating on the methodology and on the capacity definitions that are shown also here below in the citation, in the references. But here you can see, let's say, an overview, and again a way how the theoretical or potential capacities are built up in a volume on the right-hand side for different countries. So again here, this is quite a large quantity of storage capacity that could potentially meet the demand for storage in the future, in 2050. In this case, through various modeling exercises, empirical conversion factors or relationships have been defined for these gas storages, which provide a conversion from gas storage to hydrogen storage. And these are validated with analytical models, which are based on an inflow-outflow performance relationship. Now, this is something I'm going to briefly explain in this slide here. So normally you have more analog methods where you simply have a formula for static parameters that you combine and you obtain a volumetric. You can also go for an analytical model where you have gas equations for gas flow in porous media and tubing. That is the way that is explained here. And then you have also a numerical approach, of course, where you build a reservoir model in Eclipse and you can do a full numerical modeling of the storage. That is a very, very intensive and high effort exercise, so you don't do that for big portfolios. But the analytical model allows for a quick portfolio analysis. And here we can see how it works. Actually, there is a relationship for the bottom hole flowing pressure, and that is at the initial state with when the reservoir is still on full pressure. You can see that if the bottom hole pressure is really as high as the reservoir pressure, then you have zero flow. You have zero withdrawal rate, of course, because the pressure is equal in the well as it is in the reservoir. But if the difference in the bottom hole pressure is a maximum, so that you have a zero bottom hole pressure and then just the reservoir pressure, you would have maximum flow. And that relationship is shown in the blue line here. And then you can do the same for the tubing. So you have the bottom hole flow, the bottom hole pressure in the tubing and the pressure on the top. And from that you can draw another line, and that is the withdrawal line, the outflow. And if you combine these, and on the crossing points, you could determine what is the theoretical maximum withdrawal rate for the given tubing. Now, over time, the pressure will decline in the reservoir, so you get the dashed lines. And when the dashed lines are coming to a point where you have the minimum withdrawal rate, you have reached the bottom, let's say, of your operational range of your storage, and that will be together then lead to a possible working volume estimate. So that is very briefly explained. There's a lot of there's also descriptions of this in various papers, and but I'm not going to go through the formulas here because it's quite complex with all kinds of things like compressibility and non-Darcy flow components, etc., etc. That's too much, but at least there is a tool that can calculate these kind of things for a whole portfolio. And that looks like this. So here, for example, you have the Dutch case where we have done a full assessment of all the gas fields in the Netherlands, taken these parameters that are going into this inflow-outflow performance with a notional design, given well, at a given pressure, etc. And that gives you an estimate of the working volume, cushion volume, withdrawal rates for a single well, and then and of course the ratio for cushion and working gas. And that is shown here. I'm not going to elaborate it, but it was just to show that you can do this and also quickly perform all kinds of sensitivity analysis by varying these relationships. And you can test them again, and we did that with numerical models to see if the model is correct. Now, last slide here, main findings and discussion. I would say underground storage is still emerging as a technology and not commercially deployed in the energy system yet. And the technical challenges here relate to the determination of the biotic and abiotic reactions, the storage integrity, and the flow and the impacts of storage in the reservoir. The European demand of underground hydrogen storage in 2050 is expected to be comparable or even higher than what we have for present-day underground gas storage. And the challenge may be in the fact that we need to require and rapid and timely upscaling of sites. Please note that we still do not have commercial sites, and the lead times are very long. So 20 to 25 years is over in a blink, and we still need to develop a huge amount of storage. Recent European studies and national studies reveal ample theoretical storage capacity, so that there's enough, although challenges exist for the practical and matched capacity. So we need to do the spatial planning, the societal aspects, and also the link to the market. No standard methodology exists for estimating storage capacities and performances, so you need to know what kind of service the storage must provide, and then you determine the criteria for assessing and ranking your sites. So a bottom-up approach is more difficult, and it's more standard to do a top-down approach where you have a certain demand profile, and then you seek your capable storage reservoirs. Sites should be selected and tailored to match the expected demand profile. So that's what I said. That's the injection production rates, the volumes, and the cycle frequencies. And last but not least, the volumes are divided in a working gas and a cushion gas. So you need to make that distinction. You cannot work with total volumes just. And please note that the first determines the operations and the latter increases the capex. That's it. I'm going to stop here and thank you for your attention. By the way, it's okay to share my slides for those who want to read something afterwards.
Perfect. Thank you very much, Serge. We have one question in the chat. There was already a discussion going on about the last point you made, the cushion gas. Could you please say just briefly a couple of words about what is a typical cushion gas?
Now, preferably you use the same gas as you have in your working gas. So you could say I have hydrogen as cushion gas both and as a working gas. But having a large amount of static hydrogen not contributing to operations is very, very expensive. It's already challenging to make a market and a business model for the working hydrogen gas. So sometimes you can think about different gases. So typically people think about having methane as a cushion gas. That could be the driver. So you could have a partially depleted gas field, for example, and then run the hydrogen on top of it. But then you need to consider the mixing and the diffusion of the hydrogen and the methane. And so that's going to deteriorate possibly your gas, or maybe enrich it in terms of energy, of course, because you get more higher energy in there. And other things that are being considered is CO2 possibly as a cushion gas. So you can have a kind of a storage of CO2 first, and then keep the cap for hydrogen storage. Again, you have the mixing. If you have the right biotic reactions, you could see that hydrogen and CO2 will go through a process called geomethanation, and that will result in the formation of methane. So that could be another solution, but that is still very conceptual, I think, and deserves a lot of research before we consider that in practice. I see a hand from Carrie.
Thank you. I'm afraid I wasn't adding to that topic. I just wanted to say for the High Stories project that we did collect a lot of new data as well. So we didn't use the CO2 stop database exclusively. We also collated an awful lot of data. We had 965 traps at the end that were checked by the High Stories partners. And we had basic reservoir data from 70 to 80% of those, which enabled the capacity calculations across all of Europe. So we did use the CO2 stop data to infill on the High Stories database. But thank you. I just wanted to clarify, because there was so much work done by so many people looking at all of this data to make sure it was good.
And my apologies, Carrie, for not having explained that appropriately, but indeed, and there's I think also a very nice set of reports explaining that. And indeed, the C2 was just a starting point, but it has been extended considerably indeed with a lot of data. So yeah, good point to make also here, and to clarify that. And apologies again. Yeah.
No problem. There is also another big report coming out on the geological assessment, and also the web GIS is online. So it's all there for people to have a look and to browse the High Stories capacity. And thank you, Serge, for introducing it.
I invite everyone, urgently invite everyone even to visit this website, highstories.eu. And there you can really find a wealth of information and great results that have been produced. So yeah, I would really recommend to read the reports, because there's a lot of information in there that is new and yeah, will help.
Yeah, thank you very much, Serge and Carrie, for your comments. And then we will move on to our next talk from Stefan Knopf, from the Federal Institute for Geosciences and Natural Resources in Germany. We move to another topic, CO2 storage now. And please, Stefan, tell us more about the existing methodologies to estimate the CO2 storage potential.
Yes, I will. So I have to share my screen. So do you see it?
Yes.
I'm going to put you here on the right. So
it is in the presenters, not in the presentation mode.
It's not in the presentation mode. Oh,
if you could switch.
Yeah. So I guess I have to stop it again. So I think it must be the main. It is the main one. I don't understand it.
Yeah, perfect.
That's okay. Sorry for that. So do you also see this bar on the top? I'm not sure. So again, yeah, I want to give you some background information on the estimation of CO2 storage capacities of potential saline. Do you hear me? Yes, yeah. So I was not just sure.
Yes.
About the capacity of a potential saline aquifers and hydrocarbon fields. Right at the beginning, I give you a short introduction on the main principle I'm talking about, that we are all on the same page, because I don't know if everybody of you is familiar with CO2 storage concepts. And then I go into the saline aquifers, a little bit on the methodology, an overview of the methodology, and some words about the storage efficiency, and also an example from BGR from Germany. And then the hydrocarbon fields, oil and gas fields, how can we estimate capacity there? The general methodology, there are two versions of it. And finally, a little bit an outlook kind of question for GSEU at how to do then to do the capacity estimation in GSEU. So right as an introduction here, I'm only talking about the storage of CO2 in the pore space of rocks, volumetric storage. So we do not consider any caverns, and I'm also not talking about storage of CO2 in basaltic rock formation in Iceland. So here is a good old sedimentary rocks with the pore space, and we want to inject the CO2 into the pore space, which is already occupied by formation water. If you inject the CO2, it has a lower density than the formation water, rises to the top, so you need a seal. Reservoir seal, as it is in this rock sample here, we all sometimes use for students to demonstrate it. Here, the sandstone, the reservoir rock, the porous rock, and on top, the barrier, in this case, the clay stone. Yeah, saline aquifers, so are porous and permeable bodies of reservoir rocks, mostly sandstone, could also be carbonates, and they are saturated with salt water, with highly saline water, what we call also brine, and this saline water is unsuitable for consumption, so nobody is really interested in saline aquifers, except the thermal energy that is stored into the formation water, of course. And if you look into sedimentary basins, the saline aquifers are quite widely distributed there, so offers you quite a lot of opportunities for CO2 storage. Okay, so we are focusing on the pore space, and that is also defines the general idea for the CO2 storage capacity estimations in the pore space. So we want to estimate the mass of CO2 that could be physically stored in the pore volume or in the pore space of the reservoir rock. So we only consider physical and volumetric trapping mechanisms, because during the injection phase, or the 30, 40 years injection phase, injection period, they are the dominant trapping mechanisms, and that's what we are focusing on. So in general, all the estimations, the volumetric estimations of storage capacity, they have more or less the same formula. So we have mass of CO2, and then you need the pore volume of the reservoir rock, the connected pore volume of reservoir rock. That's volume. This is so-called, if you will, our tank. Yeah, the connected pore volume that have it, and then times CO2 density, and you have volume unit times mass unit per volume unit gives us mass. So this is then the mass. If you fill up 100% of the pore space with CO2, that is a mass. And then there's times ... something comes after this, and that is I will tell you about more in a minute. But before we go into details, just having an overview, if you are interested in this issue of capacity estimation studies, there are a myriad of papers, of reports, of atlases and databases. For example, the Atlas of the United States and Canada, the Atlas for the Norwegian North Sea. They have also then one for Barents Sea and another offshore areas. Also, South Africa has an atlas. There's a database CO2 store from the UK. And then the good old EU projects, GeoCapacity and CO2 Stop, that were about capacities in Europe, and we're also building up upon these old EU projects today. Now let's go into the main methods. In the EU GeoCapacity or CO2 stored reports, they mention a few and they describe a few methods. These are the two main methods. They both refer to connected pore volume, so that is our tank, or the connected volume, and the application of a storage efficiency. That's the one thing. And let's go through the formula just very shortly. On the bottom right, you see here the map. This is maybe our assessment unit. In this case, is the Mittelbund-Sandstein in the German North Sea, or on the central German North Sea part. This shall be our assessment unit. The first you need is the area, because we need the area of this. And we all assume now that it's deeper 800 meters and it's sealed on top. So area times the height, or I would call it rather thickness of the entire aquifer, and then the vertical net to gross, so only the cumulative sandstone thickness of the suitable sandstone in this complete gross thickness of the aquifer. So this gives us 8 times H times net gross gives us the volume of the suitable sandstone rocks, times porosity gives us the connected pore volume, then again the CO2 density, and then finally our storage efficiency. Because we know from the beginning we cannot fill 100% of the pore space. There's always something that prevents something. I will come to this later. So we need a storage efficiency which describes the fraction of this connected pore volume which could be finally occupied by CO2. We already know that it's not 100%, so we need a storage efficiency factor. Another method, it's more or less the same as before. Also here, the connected pore volume, that's always the same principle. We need the connected pore volume, but this time you do not use just the storage efficiency. You assume here that this system is closed, the entire area system is closed. You cannot displace any water from it, so it's a closed system. Only compressibility gives you room for the CO2, and you have a maximum allowable pressure increase that you can put to this entire system, and that defines here at the end the fraction of this 100% pore space what could be used finally. So now comes a very heavy slide, and no, don't worry, I don't go into the details, so I just will show you there's a lot of behind efficiency. Storage efficiency represents a lot of effects, cumulative effects, as I wrote here, like heterogeneity of the rocks, of the reservoirs, buoyancy, sweep efficiency. And at the USGS, United States Geological Survey, they were thinking about how can we express the efficiency in separate terms that that represent or that reflects all the various effects that goes into the storage efficiency. And again, I don't go into the details, just shortly through this formula. So they start with a net to total area. So they have in a way not only a vertical net thickness, they have a net area. So because they believe the entire area of the aquifer, you cannot use all areas. There are some parts which are not good and not suitable. So they have, if you will, a lateral net to gross. Then they have the typical vertical net to gross to have the suitable sandstone rocks, and effective versus the total porosity. And this terms used to define the potentially suitable pore volume with an assessment unit. And this unit could be over an entire basin. So this could be here basin scale. So then furthermore, another factors they call volumetric displacement efficiency. They have some separate like area sweep efficiency, vertical sweep efficiency. This is more in the area around the injection well. So how good can you reach the entire pore volume around the injection well? How good can you displace the formation water from the injection well? And these are various factors, with again what they call volumetric displacement efficiency. And then finally also a microseismic displacement efficiency. This is even on the pore scale that refers to irreducible water saturation in the pore. So the main message here is there's a lot of behind efficiency. There's a lot of what affects efficiency. And just that you have it on your mind, it's not that easy. And one last note: the efficiency is not only dependent on the on site-specific or regional or aquifer rock-specific parameters. It is also influenced by the number of injection well, the location of injection well, the spacing, so the injection strategy. And if you do an assessment of any regions, how do you know that some operator will in the future, what kind of injection strategy that they will select? I don't know. So it also gives you an idea. You cannot predict precisely the efficiency, but you can make a range of it could be. So here we are here in the static world. All this I'm referring to are the static capacity estimation. If you want to have better information about the efficiency, then you have to build a 3D model, a detailed 3D model, and then do dynamic modeling. So a few words about storage efficiency. If you go into literature, you see mostly the storage efficiency values for regional storage efficiency for this regional bulk estimation. So 1 to 4%. It's always in that area, 1 to 2, maybe 4%. But if you look into trap-specific storage efficiency, so if you have single traps where you can displace the water from the trap to the entire around volume of the total aquifer, so then you have higher storage efficiencies. For example, here 4 to 70% by Gorocki et al. It's based on numerical simulations regarding various lithologies and depositional systems. So here for clastic and shelf, they say, oh yeah, a trap-specific efficiency could range between 4 and 17% over the P10 to P90% probability range, or Goodman says 3 to 10%. That's maybe that you have an idea of trap-specific efficiency versus regional efficiency. And this is an old example from GeoCapacity, from the old EU project. Back then, they defined a rule of thumb for the storage efficiency, for the trap-specific storage efficiency. This is a top-down view on an aquifer structure. And here in the case 1, this aquifer is completely hydraulically connected to the surroundings. It's all good permeability all around. So you can, here on the injection well, displace the CO2, displace the formation water that was already in there to all the sides. There you have a high storage efficiency for high quality reservoirs. So with high porosity permeability, they set it up to 40%. That could be the value. And if you have more semi-closed condition, if you have various types of traps which are not completely open, which are maybe sealed by faults to the side, then you have less and less storage efficiency. And if you have a completely compartmentalized, sealed from all around, from all sides, sealed structure, you only have a very little storage efficiency because you only can use compressibility. And for low quality reservoir, they consider it from 20 to 3%. So these are, and if you see here for 17, 3 to 10%, I think it's also quite in a similar way. Only this high quality reservoir, I'm not sure, but here at BGR, we mostly use 5 to 20% for our estimations. So here's an example from BGR. This is the same assessment unit, and when we would estimate the storage capacity for that area, we would not do it for the entire aquifer area. So we would go and would identify and map storage structures, mostly those anticlinal structures, and then do this formula for each and every of these structures. We just coarsely characterize these structures because it is still a regional assessment. Yeah, so in a regional assessment, we go to the traps, but only very coarsely because it has to be sufficient for regional assessment. You know, that's what we are doing here. And then you have, we use here the same formula, but we have a trap-specific efficiency factor. As I said, it's 5 to 20%. This is, for example, it's an example from the ongoing project GeoStore, where we estimate the storage capacity of the German North Sea. It's a new estimation, and it's due next year. The project is over. And just about a slide also in this project. For all those parameters here, you do not have all the parameters, the exact value. So there are a lot of uncertainty, parameter uncertainties, and therefore we reflect these uncertainties that we're doing Monte Carlo simulations. As you can see here, so we have a variation of the values that are used for each single structure. But in the end, we unanimously use an efficiency of 5 to 20% here with a uniform distribution, because we do not know what could be more probable, the lower one or the higher one. So we just do it 5 to 20% here. So that was just an example. I cannot show you the result yet, but it's here about the methodology and what we have done. So now, shortly to the hydrocarbon fields. If you do estimation of CO2 storage and depleted hydrocarbon reservoirs, I don't want to go too much into details. On the right side, you see an old image with the various types of structures, stratigraphic and structural reservoirs, where you produce the hydrocarbons. And the general assumption for a capacity estimation is that the volume previously occupied by hydrocarbons in the reservoir will also be available for CO2. So the produced oil or gas volumes are assumed to be replaced by the equivalent volume of CO2. So kind of the in for out principle. What was produced could be put back in the form of CO2. And so if you know that, so we need to know what has been produced. That's or what will be produced. Here there are two methods. One is here from the Carbon Sequestration Leadership Forum, it's from Baccio et al. 2007. They had a little simple formula for gas fields and oil fields. Basically, first they need the original gas in place or the original oil in place. So that is what was originally there. So. And then the recovery factor would give you the fraction of this original gas in place that could be produced. And as this original oil in place and oil in place is reported for surface conditions, they also need gas formation volume factor or oil formation volume factor, which converts surface conditions to the reservoir conditions, because again the numbers here are reported for surface standard conditions, not for the reservoir high pressure, high temperature in the reservoir. Yeah, so this green area reflects the reservoir pore volume occupied by the producer of the hydrocarbons. That's what will be produced or what has been produced. And then you apply again the CO2 density, that CO2 would have under reservoir conditions. And then you have an estimation of the capacity based on original gas in place. Another method is used by BGR. We use the so-called production history approach. It is possible if you have reliable production numbers for each field, and then it is a very more simpler approach we use. So also the mass is the proven ultimate recoverable oil. If you have already depleted field, you know from all those reports what has been produced there, so you know what has been produced, and then you have an estimation of the gas formation volume factor or the oil formation volume factor. So that is also reflecting the reservoir pore volume previously occupied by the produced hydrocarbons, and then you apply the density of CO2 and you have the mass. In case you have still an active field, so you're doing an assessment for an active field that is still producing, then you only have the reported cumulative production of hydrocarbons so far until this moment, and there's a remaining reserve. So then you must make an estimation or a best guess for what are the remaining reserves if you don't have the data. Just very shortly here, an example from Germany, when we have to make a regional assessment of the natural gas fields. We base our the main base data is from these annual reports that are issued every year by the Geological Survey of Lower Saxony, and there you can, for each field, the production of the year and the cumulative production since production start. And then we select only the natural gas fields that are bigger than have a cumulative production of more than 2 billion cubic meter. That equals roughly 5 million. The 2 billion cubic meter equals roughly 5 million tons of CO2, because we say after lower than 5 million tons might not be that interesting. So we cut it off. And this for this bigger gas field, then we did for each field the production history approach. And as we didn't have any site-specific or field-specific remaining reservoirs, but there are information about the total probable and proven gas reserves for a producing region. And you have also information of the accumulated gas production in the same producing region, and the ratio of both gives you some example. And we use this ratio also then for each single field. So that's our best guess for remaining reserves. Yeah, that was pretty much it. Yeah, again, Outlook, I have more questions. So because we also we need to think about how do we do it, and for GSEU, for example, for saline aquifers. Regional estimation, do we do it on the bulk volume, or do we also have trap volumes, or both? Should we define also rule of thumb values for efficiency factors, or doing the pressure compressibility approach, or both? What about net to gross factors? Anything to define some default values? Also hydrocarbon fields, should we do the original hydrocarbons in place method, or the more simpler history approach, or both? What about parameter uncertainties? Kerry will also talk about it a little bit later then, and how to deal with heterogeneous geology and data across borders. That's also because we're all not on the same level if you want to do the pan-European maps and pan-European estimations. So it is also a thing we have to think about. So thanks for your attention. Sorry, I was a little bit longer, I think.
Don't worry. We still have time for one short question, if there is one from the audience. I don't see anything in the chat yet. If you have a question to Stefan Knopf, then please raise your hand. Okay, no question from the audience. I have one short question. How can you actually assume or determine the efficiency factor for the saline aquifers?
If you want to, did you say, well, it's assumed, yeah, we assume it.
Yeah. Is there any way to...
with dynamic simulations, you can have to make an expression about it. You need to reflect the dynamic processes, various injection rates and all this, and processes that happen in the aquifer. But for the static thing, we can only do the best guesses or assumptions, reasonable assumptions, scientific reasonable assumptions, right? So it's not out of the blue. So we have an idea about that. But if you really want to make a statement about a really good efficiency factor, then you must do dynamic simulation. But even then, you don't have the exact one. You can only, in my opinion, you know the exact storage efficiency only after the end of the storage phase, after 40 years or so. Then you know how much you have injected and how much place it takes.
Mm-hmm. Okay, thanks. Kerry, would you like to add something?
I was just going to join in, because I think this is one of the key things, is being clear on how much of the storage space we think we can use and how we assessed it. I'm going to say a little bit more about that very, very shortly. But I love your remark that we'll only know after we've finished injection.
Yes, that's true.
All right,
Okay.
thank you.
Yeah.
Then,
welcome.
Carrie, your next one. Please tell us more about the CO2 Stop project and your ideas about how we can provide consistent storage estimations. Oh, now you are muted and we don't hear you anymore.
Okay, I've discovered you cannot share your presentation and then unmute yourself, or at least it's beyond my technical capabilities. So I'm hoping you can see my slides.
And we hear you perfectly well.
Phew. Okay, good start. Right, so I thought I would start off with a bit about CO2 Stop, but then talk a bit more about do some thinking on how we provide consistent storage estimates when we've got heterogeneous geology and inconsistent data. So I thought it would be good to think about that a little bit. So I'm going to talk firstly a little bit about the CO2 Stop storage methodology, and again I'd encourage you to read the reports. And then I'm going to talk about trying to do a pan-European map when you have national boundaries, challenging geology, differing access to data, etc. So for the CO2 Stop, I thought it was worth explaining the database structure that was adopted. So in CO2 Stop, we looked at all of the geology. We realised that it's going to be very inconsistent what could be provided by each country. So in some cases, there will be lots and lots of data and it'll all be publicly available, in which case you might be able to be quite precise about where you think CO2 could be stored or where you think hydrogen could be stored. But in some places you might only have a rough idea. Maybe there's some sandstone over here. Maybe there's data, but it's confidential, so you can't share all of it. And so the database was set up to try and accommodate this heterogeneous data. So we have the formations, which is just kind of like, here's a big body of sandstone that we could potentially use. We then get a bit more detailed storage unit, getting a little bit more optimistic. This is something that we think we have a bit more data, we can share this. And we had traps or daughter units. And that was where we had identified a closure in a saline aquifer or a hydrocarbon field. I have to say the storage unit layer was also used where sometimes the data was confidential and we couldn't, for example, share the exact outlines of oil or gas fields. So I just thought it was worth setting out that the database was set up in sort of 3 tiers to accommodate the heterogeneity of the data, which might be caused by a lack of data being collected or might be caused by data being confidential. So for CO2 Stop, they attempted what was called at the time the technically accessible storage resource. So I think this was based on the USGS Atlas thinking, which was considering how much of the storage unit you could actually use. Now in CO2 Stop, they wanted to look at a very sort of large regional estimate, and they considered a storage unit to be essentially the part of the sandstone formation which is below 800 meters and has got a good cap rock. So they really considered quite a very broad area. But within that, they said there's going to be some spots that have got hydrocarbons or have closures in saline aquifers, and those we think could contain more CO2. Those will have a higher storage efficiency. And that is why we have this sort of technically accessible CO2 storage resource, which was calculated based on the storage units. And we then had a subset, which was looking at the storage in daughter aquifer units and in hydrocarbon fields. And in some cases, pressure was or was not considered, and that depends on whether the aquifer was considered open or closed. So they decided to calculate for each national technically accessible resource. So for saline aquifers, they thought about the permissible pressure increase, compressibility of the pore fluids, the rock matrix, how much pore space would be available, and the CO2 density. So to do a national capacity, they calculated for the storage units, they added on for the daughter units within those storage units, and then they added on the hydrocarbon field capacity, assuming all the ultimately recoverable reserves could be used. So this just gave us a very broad overview. And then in the CO2 Stop GIS itself, the Geographic Information System, there was a calculation engine which TNO prepared, which allowed a probabilistic estimate of the CO2 storage resource in structural and stratigraphic traps to be calculated by users. So that gave the users a bit more control over what was being added into that, so they could do their own storage capacity estimates. So I would very much encourage you to read the reports, because again, the methodology is quite complicated, quite variable, and it's definitely worth looking at to understand in detail how the capacity was applied and what we were actually saying. Which kind of nicely leads on to my next part of my talk, which is about heterogeneous geology and data. So what do we want to achieve? Well, first we want to display useful data in a format that's consistent, easy to use, and easy to find. So that requires us to make upfront decisions on the database content, format, display priorities, and what are the essential data. And the reason that's important is because you want to set up the database and then you want to populate it. You don't want to be altering the database afterwards. It makes things really more complicated. And I'm also going to say a little bit more about essential data. So for example, when we were doing the high storage project, although that was looking at hydrogen storage rather than CO2 storage, we had to think about which criteria were really essential. And in that case, we picked out the ones that would allow the capacity calculation. So we said to everybody, okay, we know you've only got limited time, so let's focus on those. You have to think about what kind of format, what kind of terminology and units are you going to use. I cannot tell you how long I've spent in databases correcting between decimals and percentages for porosity, for example. Just simple things like that can really throw your capacity calculation off because you realize that there's an error in the database. And we have to be very consistent with our definitions and approaches. So you'll run into fun things like for example, in the CO2 stock database, you have aquifer daughter units and you have hydrocarbon daughter units. So how would you categorize a saline aquifer that was now used for natural gas storage? Which category would you put that in? Just this kind of consistency of approach, and that's kind of where the fun is, because geology is not simple, it's not straightforward, it doesn't fall into nice little boxes, but your database is a series of nice little boxes, at least if you want it to be searchable. So you have to think about how you're going to populate all those boxes in a consistent way, and that's why webinars like this are so important, to start these discussions off, and then for the whole project to go away and have a real think about how we're going to do this, how we're going to make it useful, how's the data going to be used and searched. And of course, some of the decisions are going to be based on who's going to use the database, who is our target audience, who do we want to be able to use the data. And then that's one of the challenges. We have to think about who's going to use it, what are their competencies going to be. So if we say to people, we've got a storage efficiency of 5%, what will they understand that as? Oh, my screen's just stopped sharing. Was that me or was that you?
Might have been you. I did not intentionally do anything.
Okay. Help. Okay, I didn't touch anything. It just suddenly disappeared.
You can try to bring it up again.
Oh, there we go. Okay, I'll sit even further back from the desk. So we have to think about who's going to use it and what are we trying to communicate, and to make sure that the message is really clear. So this is I think one of the things that we've talked about with our CO2 storage capacity in Europe. We've said it's huge, there's tons of storage, and that's been really helpful in getting people interested and invested in CCS. But then we have to be able to say, yes, but you can't use all of it. And sometimes that can look like a negative message. So as geoscientists, we're all very familiar with the storage pyramids that were shown earlier. We're kind of used to the idea that, you know, you've got this resource and you can't use all of it, but we have to be very careful how we communicate that. Other challenges are variable data availability. So it might be confidential, there might be no data required, and of course, data quality. So if you're looking at paper-based records from, I don't know, the 1930s or 40s, they might not be quite as well recorded as something that's been recorded with all of the modern technology available, or it might not, depending on who's been collecting it. One of the big challenges as well is differences in interpretation. So when we do, for example, we do call it seismic interpretation. That means that what I see as a closure in a saline aquifer might not be what you see as a closure in a saline aquifer. So there's going to be some variation in interpretation and also in confidence. So you might find that you look at a region and you might have 30 years experience under your belt and you go, okay, I feel very comfortable making this assumption. Whereas if we have less experience, if there's fewer data or there's less experience in that area, you might say, actually, I don't feel very comfortable. I'm going to be very careful what I put into the database. So it can be, there's a whole sort of range of sort of human factors that play into this. Of course, geology likes to be variable. I think this is why it's so important to go and look at the rocks, because you go and you see the rocks and you remember that you might be putting this into your model, and your model sort of blocks might be 50 meters cubed maybe, or they might be a few meters cubed, and that you're trying to communicate this huge complexity into modeling. But I will leave that to the modelers because that is definitely out with my expertise. And of course, the variable methodologies to assess capacity, which is partly why we're here. So in terms of the upfront decisions, we need to think about what we're trying to communicate and who's going to use the database and what are they going to use it for. So something like CO2 stop or high stories gives you a fantastic European overview. But if you are the storage operator, you are going to need a lot more information about a site before you can go and invest in that storage. So you kind of have to think about, we've got the whole scale from pan-European to a little corner of perhaps the North Sea where somebody wants to store CO2 and they need to know everything about just that little spot. In terms of us developing the database, we need to agree up front on the parameters we're going to use, and things like, are we going to screen sites so that some aren't added to the database? So this could also be an interesting topic, particularly when you're going into something new. So for the high storage project, for example, we started off with the CO2 stop data, which had been screened at 800 meters. But of course, for hydrogen storage, that isn't the limits. We can store hydrogen more shallowly than that if we look at underground gas storage as an example. So then we have an argument about, so what's the minimum depth? Or we might discuss, so what's the maximum distance that you could be from a CO2 source or your user of hydrogen or natural gas? Are you going to use that to screen, or are you just going to say, here's all of the data I've got, let the policymakers make the decisions? Think about which parameters are essential for calculating storage capacity. And will you make assumptions or interpolate so you can provide estimated capacities where there are poor levels of data? So that's kind of something to be agreed and discussed up front so that you're trying to take a common approach. And again, it comes down to the expertise of the people who are populating the database. And then we have to think about how the data is going to be displayed and how you show data versus interpretation, because that's also worth thinking about. So the porosity of the rock isn't going to change, but my storage assessment might as I learn something new or if I develop a new methodology. And I will just mention, considering how the data is going to be displayed and working that out up front is kind of useful, because we got towards the end of the high storage database. We thought, hey, wouldn't it be cool to colour up the traps by fluid fill? And then we realised that it meant that we had to we had to go through the whole list, check everybody had filled in that field and that they'd filled it in consistently. It's worth kind of thinking about up front what the end point you're trying to get to in terms of the database and the display. Challenges, variable data availability. So we've all run into this many times where the data is confidential, some are behind paywalls, and some require more effort to extract and interpret. So you might be going to an area where you've already done a lot of interpretation, or you might be just starting out scratch and you've actually got to get out the well data, tie it to the seismic data, and do a full interpretation. We have had cases in the past where the interpretation but not the raw data can be shared. And sometimes the location or the outline of an oil or gas field might be confidential. So how do you display that data? Do you put a point in the middle where you think it is? Or you can end up with a horrible situation where you've got some data, but you can't tie it to a location. So you just sort of kind of like click on the country and a whole list comes up. It's kind of worth really thinking about how you're going to display the data and how you're going to manage the data gaps up front. I will note a couple of points of caution. So data on the seal is generally harder to find than the reservoir. And also beware of data bias. So people tend to take samples out of the best bits of the reservoir. If you're not careful, you can end up with a much rosier view than is actually true. And something else I will also say is how to avoid lots of blank fields in the database. So this is always a problem. When we've got the data, we know we're going to get a lot of the basic reservoir data, but it doesn't look great if you have an entire database with lots of empty fields. And it's just making sure, how do you optimize that database? How do you make sure you've got all of the essential data, but that you're asking a reasonable level of data so that people can fill it in? As I mentioned before, being consistent is really critical. So for the database parameters, sort of confirm and communicate the units. If you've got lists, this is great if you want to search the database, but it really upsets sedimentologists because they want to be much more precise. So I'm a geophysicist. I'm kind of happy with sandstone, you know, maybe a bit of description of the minerals in it. And you have to consider how you're going to balance the needs for having a consistent list so that people can select and you can search the database, to being flexible enough that will allow geoscientists to populate and communicate the geology effectively. Thinking about how you categorize the potential stores and what do you consider a potential conflict of interest. So would you consider a site that was already used for natural gas storage as a conflict of interest with hydrogen storage? So do you think it's likely they would convert to hydrogen storage? We don't know the answer, but it's just the kind of thing that you might include in the database. And of course, geology is always challenging in terms of fitting into nice little boxes. It's worth noting interpretation is interpretation. We can't look at the deep subsurface, so we're relying on our interpretation, which has to be done by the experts, and we're relying on that expertise to provide useful data to enable policy decisions. The way that data is shared is often variable. So you get you might have to consider, do you have minimum, average, maximum, most likely, have to communicate a range of values and how you populate that. And something else that's kind of interesting, when you're representing the data in a map format, a GIS perhaps, how do you represent stack storage when you've got multiple reservoirs on top of each other? And of course, because we're here for capacity, to say that the variable methods to assess capacity are also a challenge. So there's really multiple approaches, and the most important part is being really clear which is in which part of the equation. So Stefan shared some very simple ones from the CSLF there, and somebody pointed out to me earlier, well, if you've got the thickness of the reservoir, something very simple, have you already multiplied that by the net to gross? So you've already, is that the gross thickness or is that the actual thickness of reservoir rock that you've got available? And sometimes those two things are combined. So when you're putting your storage efficiency on, if you're not careful, you can end up multiplying more than once by different factors. So it's really important to be clear what's in each part of the equation, what your assumptions are. So in summary, I agree up front the aims of the database, the target audience, the essential parameters, and how the capacity is going to be calculated. Good luck. The database needs to be tailored to meet these needs, and we need to set out clear guidelines on how we're going to populate the database. So we need to be absolutely clear with the people who are working on the data to make sure that it's as consistent as possible. So good luck, and thank you for your time.
Thank you very much, Carrie, for pointing out what kind of work there is ahead of us. Before we start with the discussion, there is one more question in the chat. You talked about the storage unit with a depth of 800 meters. Is this threshold also valid for CO2 with a large percentage of impurities?
Oh, that is a good question, because impurities would significantly impact. I'm afraid I'm going to have to pass that one to the geochemists and the modelers. I understand that adding impurities does significantly move the CO2 curve in terms of when you get to a highly dense or supercritical fluid. So sorry, I can't provide an answer on that one.
All right. Thank you. So thank you all very much for your attention to the talks, and thank you for presenting your ideas and the current state of the art, more or less, what is available about to estimate the storage potential. I would like to start the discussion with the question if there are any methods missing. Is there anything missing that you want, that you know, or that you would like to add in our project? regarding the estimation of the storage potential? Is there anything that was not presented here? No remarks?
Sorry, Cornelia.
Yep.
I had a question for Curry, if you don't mind.
Oh, go ahead, please.
Thank you. So you mentioned briefly in your presentation, I don't know if I missed it, that you were considering a pressure limit for the reservoir. I understand that for especially CO2 stop the database, you're not planning to do site-specific, fully dynamic, complex models of each reservoir, but it's more of a first-order approximation on these daughter units or the storage units that you mentioned. So I was wondering if you have a rule of thumb for that pressure limit, if it's going to be based on the original reservoir pressure and maybe a percentage of it. Well, yeah, and that's maybe another question for me.
So for CO2 stop, they used a fraction of the a percentage of the fracture pressure. So I believe they used aimed for 90% of the fracture pressure of the reservoir in terms of what they considered the acceptable pressure. But yes, it is an interesting question. And one of the reasons that they mentioned pressure was because they were calculating across these large storage units and they only used the average pressure. So they thought about kind of one of the parameters in the database was the average depth. But that's if you're calculating the pressure at the average depth, what that doesn't allow for is a very large storage unit that might have shallower bits. And of course, if it goes much shallower, then you might find that the pressure increase in those shallower parts is unacceptable. So it was something they flagged in the report as we've got a large unit, we've done an assessment on its, sort of to give you an idea of the capacity, but it does come with a lot of caveats. And I think one of the pressure does become particularly important when we start to think about how the traps will interact with each other as well. So I definitely think that whatever we do in the Geological Service for Europe project, that we have to consider how pressure will impact our storage capacity and how it will impact neighbouring storage sites.
Bruno Saftic, please go ahead.
I have a question regarding storage efficiency factor. I think this is mostly for Stefan Knopf. Hello, Stefan. You have shown the table of the approach that was taken for structurally defined aquifers in the EU geocapacity project. This is the one that we used to call the cartoon approach.
Yes, it is.
There are two levels of percentages that you might take, and one is connected to the high quality reservoir and another to lower quality reservoir. And I was looking at the report recently. I was unable to find exactly the threshold or an orientation what would be the high quality reservoir and what would be the low quality reservoir.
Yes. The same for me. I don't remember. I think there is no threshold. I think it's something like, as you said, it's a cartoon approach. So you leave it to the geologist. Is it more high quality? Is it more low quality? If high quality is Sleipner with, I don't know, 30% porosity and 3 Darcy, that's very great. Then everything else is more. So for us in Germany, we also consider that we are more on the downside, not the best, the very best conditions. So I would always say rather lower quality, but still quality to store, but maybe not on the very high, on the high end as Sleipner is.
So each cartoonist has its own approach.
I think so, but I could be wrong. But I also looked at it and I also never found any threshold for this.
Maybe somebody else remembers the project exactly. There are some.
Yeah, I think there are also some from the old.
Who were looking at this for the first time. It was in Estonia when we first saw this and then had to deal with it.
Okay.
Okay, thank you very much.
Yeah, welcome, Bruno.
Bye.
Are there any more questions to the presenters? No, okay. I'll try again with a question to start the discussion. What do you, when you do a storage estimation, need the results for? So who is the end user? Who are you going to provide the results to? Alexandra Dudu, please go ahead.
Yes, so we have contracts for estimating storage locations for different companies, that emitters, for example. And the authorities are also interested in these storage capacities lately.
Which authorities are those?
Dealing with CO2 geological storage. Competent authorities for CO2 geological storage. Lately, they are interested in making storage atlas for our country.
Okay. Carrie, please go ahead.
I was going to say, I think that this needs to be something that could be understood by policymakers in terms of how it's displayed. That would be the end goal, would be to display something clear and consistent that policymakers could follow. But then the geoscientist in me wants to have lots and lots of data underneath so that I can look at the lovely data too. So I'm a bit conflicted here, but I think that we have to make something that's in the GIS, that's something that's easy to use, that communicates to policymakers to help them make strategic decisions.
Good point. Serge?
Yeah, maybe also following up on what Carrie says. So in one way, we make nice maps and we show where what is possible and how much we can store. And this can in itself be handy to see where you could develop certain actions or not. But let's say if we have a spot on the map or a stain on the map where there's a potential storage site, and then I'm coming back to what Carrie says, there are some decisions on that. And what might be interesting to know is, and then I'm also referring to what has been established as the storage readiness level. Where are we in the development, in the maturation of that spot on the map? Can we say something about what kind of activities would be required to mature that spot? Should wells be drilled, or should even seismic be acquired? Or are we already in a stage that we could say, well, there are already wells and we are just waiting until the gas has run out of that reservoir, and then we could convert it into a type of storage that we want? How much time is involved? How much effort is involved? And what kind of alternatives are there maybe around it, either as an alternative or as an upside? And those kind of informations that can be connected to a spot, which are not per se geologically defined, will really give an action perspective, I think, or a decision perspective for any stakeholder. He can decide, okay, if I want to deploy storage on that site, I can do it here in the quickest way, or I need to account for a lot of research and long times of development on another space. That could also define the order in which you are going to develop or deploy sites. So I would say a geological map is nice. It is informative in itself, but it is not always per se informative for a decision maker. Just the quantity doesn't say much, or the location.
Mm-hmm. Any more remarks on that? We have one in the chat mentioning that in France also the authorities are the end users. Paula, please.
Yes, thank you. I would like to ask that the atlas for me is more than the map. I think that to establish a general and common capacity methodology estimation will be great and very useful also for the Commission, because can be the base for future and other capacity estimations. I mean, it's not only the map, it's also define methodologies and share with the rest.
Yes, so maps alone would not be enough in this case. Good point. And then we can also discuss about if you see a competition between CO2 and hydrogen storage in your region. Is this a point of discussion in your country or region? Serge?
I would say hardly. And I say that because if we want to store CO2, we particularly look at larger volumes. You don't want to have small volumes. So storing the large volumes would be best for CO2. You can have a long injection time. That's also economically most interesting. While for a gas storage, you would have, if you would have a gas field with a very large volume, the quantity of cushion gas that you need to inject is also very large. So the capex would rise dramatically, possibly. So you look for smaller volumes often that are less interesting for CO2 storage. So the other thing is that, well, and that's particularly for the Netherlands, storage of CO2 happens offshore, and gas storage will probably be most effective onshore, where it is really connected closely to the energy system. So that would be my reflections on this point.
Okay, thank you. Any further remarks? There's one more in the chat that if CO2 is a cushion gas, then it could be at a small in a small case a synergy and not a competition. Carrie?
I wanted to go back a little bit to the database discussion, if I may, as well, to ask about how we keep the database updated. Because if we're trying to produce something fantastic for policymakers and with more than a map, then I think one of the most challenging things is how do you keep it updated? How do you make sure, how do you add in new data? How do you keep it something that's living, that's something that's still operable? It would be very useful if we could think about something that would be easy to update if we can find the resource to do so. Otherwise you end up with a situation like CO2 Stop, where the CO2 storage kind of pan-European estimate was done 10 years ago, and things have moved on since then. We have lots of new data, we have new thinking on storage capacities. So I think it'd be really good to think about how we could keep the database updated too.
Absolutely agree with you, Kerry. It's something that we need to define also. And I think that Julie is in the webinar, so perhaps she has any other idea.
Any other ideas? Bruno?
Well, if someone can think something about having a sort of permanent, moderately funded project for this, for all geological surveys to do for every country. It can be maybe done every second year or something like that. Something similar was done in my country regarding the groundwater resources. There were at least 5 consecutive projects on the groundwater resources in order to have a control on what is happening with this. And similarly, or analog of this can be done for energy storage, whatever, in principle.
Carrie was first. Please go ahead.
I was just going to say thank you for the interesting point, Bruno. That is a really good question, whether we, and particularly now, since there are so many CO2 storage projects under development, I think it makes a good argument for continuing to update our database as projects come online and we learn so much more. Thanks.
Serge?
Yeah, if you want to have this kind of situation, I think you need to really look also in the direction of legislation. In the Netherlands, for example, for the shallow subsurface, we have a base registry. So it means that there is an obligation to collect all the information from the shallow subsurface. And any party who wants to do something in that shallow subsurface is obliged to at least use that registry as a starting point, the information that is in there. And you could possibly think of a kind of a CO2 or storage registry that you could implement on a European scale. It would take a tremendous effort, of course, and a lot of convincing of policymakers maybe, but I think as geological surveys, technical institutes, etc., we have the capacity to collect that data, and yeah, that would, I think, really be a kind of a basis. Then you would have a permanent structure that is legally based to do this kind of work. But any project in the general sense will have a start and an end, and it will always have some point where there is no support anymore for updating.
Okay. There's one more comment from in the chat about Monte Carlo that was discussed earlier for a portfolio evaluation. How about an approach to correlations between storage sites also captured in database? Do you know of any attempts to do that?
So what is meant with correlations between storage sites? I don't.
Maybe I can elaborate a little bit here. So
Yes.
Sometimes when you look at the portfolio, you've got very many similar opportunities in a particular region, perhaps even in the same reservoir layer. Very likely, I think that if one storage site is going to be successfully developed, that has implications. It's correlated to the success of other sites as well. So how can you best, does anybody have the best practice for connecting these two and correlating whenever a portfolio evaluation of the total storage capacity of a country is being analyzed? Caprock,
I'm not sure if there's
these types of net to gross, these types of parameters, they'll likely be uncertain but correlated between different fields.
Yeah, if you have that information, of course, you can do so. To correlate, you also correlate between wells if you have information from the wells about if you're in the same, for example, in the Mittelbund-Sandstein and the Wolbrausen limestone and so in one of those parts, you can do a correlation, but you would still, I would still do a Monte Carlo simulations for each of them. But they still have uncertainties. For example, to define the spill point that defines the area of an aquifer structure. There's also uncertainty. I would always do a Monte Carlo simulation, but the correlation between sites, if I have a site and I know it's working, then of course I have also an idea on that side about porosity, permeability, and any other dynamic issues, and I could use also for my side. But I don't have an approach. I wouldn't come up now just in the minute. But of course, this is an important information if you know there's already a site which works. And if you have maybe a gas storage site, gas storage in the Mittelbund-Sandstein, we have some porous gas stores, underground gas storage sites. So you can, of course, take information from that if you have that information, of course. So might be not public.
Thanks, Stefan, also for your presentation. Thanks.
Yeah, welcome.
Carrie, would you like to add something?
I was going to comment on the interaction between sites. So I slightly misunderstood Jasper's question, but I was going to I thought it picked up an interesting topic on how the sites will interact. So I was in the ZEP working group where we had storage operators talking about potential conflicts between sites. And they wanted something a bit like the planning permission regulations, where if you've already got a storage site developed, that if anything's being developed near you, you will also be consulted and you will have discussions with the people who are trying to develop a storage site next to yours. And I thought, well, actually, that's a really good point, because if you've got one storage site in an interconnected volume, there's actually a risk you might make other stores nearby less attractive because you've increased the pressure in that whole unit. So there's a whole kind of interesting discussion around pressure and interaction between the sites, and it would be really it would be something new if we could talk about how, if we had not just the location of the trap, but we also had something about the pressure footprint. So it's not just the actual CO2 footprint, but the bigger pressure footprint and how that might overlap onto other sites.
As if one storage site would not be complicated enough, it can get more complicated adding a next one to it. All right. So are there any further questions or remarks? Because if not, then I would like to thank you all very much for your attention, for the speakers to give their excellent talks. And I'm excited to see this work moving forward in the GSU project and in other endeavors. I will send out the recording and the slides of this webinar so that you can have that for yourself to look up. Thank you very much and have a good day.